All right. So thank you everybody for joining today. We're waiting, maybe we're going to start at 1:05 to give enough time for people to join. Milos is going to be the coordinator today, and Professor Hossein from Alberta is going to be our first speaker. He is kind enough to give us a high-level overview of a long-running project there. So it's going to be a long talk, the first one, by comparison, but very interesting nevertheless. And then Milos is going to be coordinating. There's going to be a Q&A session after every talk. After Professor Hossein's talk, there are several shorter talks that we have. And as always, the talks are going to be recorded. I'm going to process the video and upload it on YouTube, and it's going to be on the same playlist as yesterday. And I will start up now. Okay, so maybe we can start today. Again, I would like to thank Professor Hossein for agreeing to give a presentation at the annual general meeting. It's going to be a 45-minute presentation plus questions and answers. Milos Nikolis has graciously agreed to coordinate the meeting today, so I thank him for that. And in order to be respectful of everybody's time, I think we should move ahead with the presentation. If anybody has questions, since this is an online presentation, maybe it's best to wait until the end. On the other hand, I'll let the speaker decide whether they want to take questions on the fly. Right? We can facilitate that. Thank you, everybody. And the talks are going to be recorded and posted on YouTube.
So thank you, Professor Andreas, for giving me the opportunity to give this overview and the introduction. I think since it is recorded, it might be best to keep the questions for the end. But if you do have difficulty following some stuff at the very beginning, I think it's okay to ask questions because with this audience, it's always a bit challenging because a smart group of people who does things on a field that is slightly different from my field, then there is, if the few fundamental concepts that we take for granted are not very clear, then the talk is a bit less useful. And I do not want it to be that way. So it's a bit informal in that sense. So feel free to ask questions if you need to, right? So that being said, I'll start this talk, and just like the title says, right? We are mostly interested into eliminating the memory bottleneck that happens in AI-based accelerator hardware, right? It's obviously a group effort, right? I have a bright group of students who worked for me, and still some of them are working for me. It's a collective work of last 5-6 years, within which people have graduated, obviously, and they are working in the industry. So I thank to all of them for their contribution, valuable contribution to this talk. So everyone can see the slides, right? If not, I guess please feel free to let me know. And everyone can also hear me okay, I guess. Okay, so here is the outline. First, I'll talk about the motivation. Although you guys working in ML applications already know the need for the memory access, right? But in general, right, if you are starting to work on it, it's good to define what problem we are trying to solve. And then, just like I said, a little bit of background on what we do would be good. The way I try to set this talk is not too much for the students who work for me in the lab or who have a strong service background. The talk is set up for people who are experts in ML hardware or applications, but they need to use the SerDes and they need to understand enough so they make the right choice. And in that sense, we would be giving the background and the overview to help that choice process. And that's why we set it up into 3 application scenarios, right? So way back when we first started this COHESA project, right, that would be 6 years, 5.5 years back, and we started writing the proposal and had put our thoughts together. That would be 2016. And that's when the most relevant problem that people would tell us was that you need to go faster, means very high data rate, over a finite number of wires or links we can think of, right? So applications were data center centric, right? And that's what we did put in our objectives, right? 5 years down the road, we are going to enable 100+ gigabit per second with the best power efficiency and provide a pathway towards 200 gigabit per second, right? And that's what I will show you where we are today in terms of that. And I'm happy to say that like we were able to build 112 gigabit per second and also make some accomplishment along our projected goal of 200 gigabit per second. But when you approach that problem, we learned a couple of things. One of the important thing is to learn is that to build such a link, the technology access that you need is actually a very high-end technology process, 5 nanometer, 7 nanometer FinFET, that we can't get access sitting in academia. That was the first realization. TSMC would not open up those nodes to not only to universities in Canada, all across the world, even in Stanford, Berkeley, they don't have access to the cutting edge technology. TSMC feels very protective about it, which means we have to have an industrial partner. And the level of complexity as well. Now, that being said, it's not that people are not building high-speed links in other technology nodes, a bit older technology nodes. They do, but the achieved performance and the innovations are somewhat a bit not aligned to the industry in that sense. So we wanted to do something that is more technology ready, that is easy to adopt, and that's why I think partnering with the industry was the right thing to do. So we did collaborate with Rambus on this one, and they were generous enough that we could publish those work. And the other thing was that when you think of what is future ahead, we have to know from the industry what is their roadmap on in terms of technology, in terms of the interconnect, in terms of the solution space. So when I explored the 200 gigabit per second, Intel was generous enough to share those channel models, the infrastructure they think of, the solution space they think in their mind, right? So they were my collaborators for this work. And while we were doing it, what I understood is that the solution space changes, right? During the grant, what we thought to be the scenario, there are things that are outside, and those application scenarios motivated us to find solutions that may not be very usable today, but at least have it proven and adoption ready. And adoption ready means if we build it in a silicon and have it measured in the lab, that shows that it is not just an idea on the paper that looks good. It actually has viability, that is actually ready to be implemented in a better technology node, achieving better power number, right? So those proof of concept applications, we did it at 20, 32 gigabit per second. Those we could do it in older technology node because the roadmap for those different scenarios are not set up, but it's still good as a learning experience. So I'll go over those things too, right? So basically, the talk will be more driven not by circuit or very advanced equalization techniques, but more driven by application scenarios that probably is more relevant to this audience, which wants to build their ML hardware, also thinking of those application spaces. And then I'll try to summarize what we discussed, right? Okay. So when it comes to motivation, there is not much to say. You guys already know it, that during the learning process, may not be so much so in inference. You have to store, update all these weight vectors and other things too, right? So if I use a metric to see where the energy goes, you will see that the most energy consuming parts are these memory accesses, right? So we want to improve it. And of course, the multiplication and other things also have room. And that's why we try to build Mac units, which are very energy efficient, right? But my particular talk today is going to be centered around this bottom two, which kind of shows that the order of magnitude higher power or energy consumed in that high-speed interface compared to everything else that's in there. So you kind of have to put it in the log scale to put it there. So I took this picture from Boris Moorman's ISSCC 2019 kind of as the motivation why we need to make these links much better. So I'll keep the motivation to there and go to the background quickly, right? So what I say, it literally means, how do I send a tiny bit over this channel to the other end? That's what basic concern is. So you can think of this RX could be memory or processor, and this could be memory or processor. By the way, you also need processor to processor links too, because in AI, you make application specific processor, and after computation, you need to send it to the other parts, right? So what happens on this side, you serialize all these data streams to time domain multiplex. You can think of it to create a stream of high-speed data that you send over the links, because the periphery of your IC is going to be limited. So the number of pins you can use to send data and receive it are also limited. So you want to make most out of each pin. That's why you need to serialize it and create an extreme high data stream that you send over this wire, right? So now think of that I'm sending this 00100 pattern, and when we say this bit width, we consider that to be unit interval, right? For example, in a 10 gigabit per second, every bit width is going to be 100 picosecond, right? In that 100 picosecond, I can send either a 1 or a 0. If you send a 1, and that would be VDD, and if you are sending a 0, that would be E to the ground, just like the digital logic levels would do, right? But when this bit is sent over this lossy channel, what happens is that this bit is going to spread out. That's what we call this dispersion, right? And this dispersion happens because this channel, if I look at its frequency response, it's going to show a frequency dependent loss, which would basically spread this bit such that where it is meant to be 0, these levels are elevated, right? And these elevated levels is what we say is ISI, or intersymbol interference, because from the ideal 0 levels, it is elevated to a level that is going to make it less detectable in a very qualitative term, if I would say, on the receiver side, right? So now if I extend this tiny bit concept to a stream of bits, this is kind of what it looks like. So I'm sending a whole bunch of random bits from the left side, and depending on that frequency dependent loss is going to create these levels appear in this way, right? So you do see that sometimes it does reach to the peak, but oftentimes it barely crosses the threshold, right? Which is basically an ideal 0, right? So if I capture all this information into a single plot, that would be called an eye diagram, right? So it basically means with this unit interval, you fold this time domain signal over and over, and that sort of captures all the possible levels the received signals 1 and 0 can take, right? So you see where and how these frequency dependent loss is creating the problem. It's kind of bringing the level 1 as low as here and pulling up the level 0 as high as here, right? So now compared to the ideal levels, you have deviated so much that what we say is opening between, or the separation between logic level 1 and 0 has kind of decreased significantly, right? And I intentionally kept it less how to say, adverse. It could be more than that. You could have the 0 even exceeding this threshold, and 1 could drop below this threshold, and then we wouldn't even have a way to detect the bit, right? So the technique that fixes this problem can be called as equalization, right? So I won't go into the detail of explaining what equalization and how do we do that. That's kind of like very SARDIS specific and not probably suitable for this audience. But as much as you guys can understand, equalization means fixing these ISI noises. That sort of understanding is good enough to organize rest of the talk, right? So now one more interesting concept is that once we receive this signal, where would we sample to detect the logic level, right? And that's where this some concept called clock and data recovery comes into the picture, right? So I'm going to send the data stream from here, and at this point I'm going to detect it with a clock, right? So you can think of this sampling process is slightly advanced than a regular D flip-flop resampling a data or retiming a data. So because your input signal is kind of not very well defined, the levels, 1s and 0s are kind of been pulled down and pushed up, you have to have something that is a bit more sensitive. And that's why we also want to sample it where we have the most opening, which would be the middle of the eye, right? And that's what this CDR does. It kind of tracks and finds the optimal sampling point, and that's where it samples. So as far as the background goes, I'm going to keep it to this point, right? And I kind of have spent about 1/3 of it on this. I do not want to spend more on this, but I think just based on these concepts, we can think of how the links could be built, and how could be aligned to your particular ML applications. Right? I assume nobody has any question to it, so I'll move on to the next part. So this is where things get a bit more advanced, I would say, the architecture choice. How do we want to decode that impaired bit, right? The simplest way would be to actually, in an analog fashion, right? So precondition the signal such that some of those ISI can be removed, right? By inverting what the channel does. It attenuates the high frequency loss, or it attenuates at high frequency. I'm going to boost those high frequency content so that the signal levels are somewhat restored, right? And then we have an analog loop that sort of just like a phase lock loop is going to center the clock to the middle of the eye. That is how the links had been developed. I would not say I would put the research work in academia aside. In industry viewpoint, that's how, like, till 2012, 13, that's how we used to build these links. And then we shifted over to something called ADC DSP based links, where we actually digitize the signal right up front. And then everything that we used to do in analog domain, we do everything in the digital domain, which becomes a DSP, equalization, timing recovery, all that. So these are the two architectural choices that we can make, and there are some pros and cons to that that I will discuss a bit later. Right? But this is what I wanted to discuss and pay attention to a bit more, right? Because there are so many ways we can choose SerDes for our ML application, it's good to have a broad level understanding on why and what to do. So this chart is built with all the figure of merits or all the desirabilities that we want to have it there. We want, for example, we want to have high data rate, right? We want to have a very good energy efficiency, right? And we want to be spectrally efficient and all that, right? But all of these comes with a cost factor, and cost factors are often as such that they are directly opposite of each other. Very good example could be the data rate and equalization, right? Just we have seen the channel, right? At high frequency, the losses are higher. So if I want to go to higher data rate, I have to compensate more and more loss. That means my equalization is going to be complex. So I cannot have high data rate and simple equalization at the same time, because they are just complete opposite, right? So which means getting closer to the center is the better it is. So if I go very close to the center, achieve a very high data rate, my equalization repels away from the center because it becomes much more complicated. And the same is sort of true, for example, signal to noise ratio and spectrum efficiency, right? Because if you want to encode more bits on a single carrier, then you are becoming more and more efficient spectrally, right? But then the problem is that the distance, the Euclidean distance between those constellation points are now going to be closer, because the peak to peak remains the same, and we have just created more levels in between, right? So the SNR and these two cannot both be improved at the same time. It has to come with a price of signal to noise ratio, right? So that's how this figure of merit thing is set. And what we will see is that some of them are not, it's not always so restricting in a way that if you say that, well, so data rate and energy efficiency, can I achieve both? Good. possible or may not, right? Because complex equalization will cost you more power, and that's where you have the room to be innovative, and maybe you could find an equalization technique that is efficient, energy efficient. So it is possible to have these two are achieved at the same time. So they're not necessarily orthogonal in that sense, right? So we will see how this scenario looks like as we go through different applications. So the first application scenario is the data-centric one that we have briefly talked about. Now, to give you a better example, if you see what is happening in the data centers, obviously it's going to transfer a huge amount of data between the ports and between the switch ports, right? And so you have fixed, centralized, and distributed, and in all these cases you will see that the data rate requirements are increasing significantly, right? These are C2M, means channel to chip to module. Data rates are approaching 400 gig, right? And top of the rack switch to server bandwidths are also reaching to 400, and that sort of requirements, right? So what happens if you take any of those, say chip to module links, those are very advanced, right? I mean, you don't need to have, traditionally these were PCB, these days they're even okay to put a AWG cable, right? So even if you put those cables, there will be loss that we cannot just simply remove, right? Even if we choose the best material, the losses would still be they are coming from the bad capacitance, ESD diodes, package loss. So when they get accumulated, you are talking about 30 dB or higher loss at a frequency of around 40 gig or so, right? And that what it says that the usable part of the spectrum is only about up to 30 to 40 gigahertz. So now if I have to send more data, higher data, and achieve higher data rate, there are two things we have to do. A, we have to send more bits using this spectrum. So move from just sending 2 level of signal representing 1 or 0, we have to send 4 level of signal that can actually capture 2 bits of information. And we have to do equalization to help reduce the impact of that ISI. And that's why ADC-based SerDes is kind of where this sort of solutions has merged across the industry, right? And that solution means that we are achieving very good data rate, but the equalization complexity will be significant, right? And we are being spectrally efficient because we are encoding 2 bits like PAM4, but my SNR is a bit of problematic, right? And then a similar scenario for the other things can also be justified, as I noted here, right? So in such a scenario, energy efficiency is 4 to 6 picojoule per bit, and that's kind of what we are trying to achieve, what people are trying to improve on, but that's where the numbers is sort of saturating. So some of these things we have to kind of think beyond these boundaries. Like, for example, when your SNR is degraded, you can't just send a bigger transmit swing from here or do too complicated equalization here that goes out of it. Then you have to do some encoding, like forward correction encoding, and that sort of coding method, Reed-Solomon, can give you the missing SNR to bridge the gap. And now that does not necessarily come for free, right? So that those add extra latency into the transmitter and the receiver that may not be always desirable for all ML applications. So something to think about that, right? And so the SNR is something important, but for the data centers, we kind of have come to the convergence that this is the way that things can happen, right? So as I said, I'm not going to go too detailed into the implementation detail. Rather, what we're going to do is more like provide what is achievable and what solution space it can serve. So in that sense, this is the hardware that we built in collaboration with Rambus, and that's why we had 4 lanes. Each of them has a transmitter, receiver. Receiver mostly includes the ADC, AFE and ADC, and then we have the DSP that sort of equalizes in digital domain in a very efficient way, right? And so that sort of justifies why we need to go to 7 nanometer, because this DSP, or the digital part, the power it consumes is significant. The area it consumes is also significant. So unless you are in those technology nodes, the solution would not meet what the users have in mind. So that's why it is very, very critical that these architectures are always built in the best bleeding edge technology nodes, right? And so the detail on such receivers we presented at ISCC, we did a demo. It can be found there. But I'll talk about the most important concept, why ADC DSP. So I talked a little bit about the technology benefit of that, why it has to be built in 7 nanometer, but the justification of the architecture comes from here, right? So till we were in the energy domain, we had some level of tolerance to the residue ISI. For example, the sample points are basically the ISI component. Ideally, ISI free would be only the middle one. And you remember those elevated level of zeros. They need not to be always elevated. It could be negative too, but there would be some amount of it, right? If I construct an energy I with this, I would probably still have some margin, but as you see in PAM4 level, these 4 levels are no longer distinguishable, meaning if I set a threshold, I won't be able to always make the decision between, or distinction between 1 and 0 with the level of confidence, meaning the BER level that we want, right? So to equalize these ISI components, the type of response I need is the filter response. This is what it looks like. And if I look at the frequency response, you can see that its shape is as such that it is very hard to realize with a single pole or single zero or couple of zeros in the transfer function. So such transfer function is not realizable in analog domain. It's only much easier doable in a DSP domain, because it can precisely place all the poles and zeros needed to create that. And then I can do cleanup jobs such good that it has only 1 and rest of them are all forced to 0. And now these 4 levels are easily distinguishable, right? So that's why the multi-level signaling, spectrum efficient signaling, complex modulation do not have a choice other than doing ADC DSP, right? So this is the implemented prototype, and what people care about is not just the power number, but the area, how closely you can pack things together, right? And when it comes to the power number, that shows the flip side of it, meaning the price that we pay for that. So now if you look at this ADC that takes about 195 milliwatt, even in 7 nanometer process. So that would set the lower limit of the energy consumption, or the best energy efficiency that we can have there, and which is kind of like 4 to 5 picojoule per bit, and it's not getting much better than that, right? So we did, this is just to show that it actually worked, right? So this is the eye diagrams, like those 4-level eye diagrams. These are on the transmitter side, though. On the receiver side, after it goes through this complex DSP equalization, I can recover those 4 levels, and if I extend them, and that is statistics that shows that the accuracy of them, or my probability of making error, is kind of less than 10 to the minus 6, 10 to the minus 7, which is just good enough for the forward error correction to clean it up to 10 to the minus 12, right? And so this is also another thing to think about. What type of BER are you looking for, right? So this type of links can only give you BER of 10 to the minus 6, minus 7. If I go to 200 gig, it might even go to 10 to the minus 5, right? So if your application can live with it, then maybe that forward error correction is not so needed for you. But if that is not, then you have to account for the latency that comes with such encoding and decoding methods, right? So now I would move to something else, but before that, I wanted to at least leave some pointers if someone is interested to know more about it. These three papers, so they are all kind of my group and collaboration work. So actually, like if you go back, when we think of the ADC DSP, the first few things we did is at a much lower data rate, right? And you would also say that, right, compared to the other groups, the people like us who has to build the hardware and measure it and then publish it, you can see that we are very slow. In 6 years, I have only 3 papers to show for, right? Because it takes time, right? And so even this project that was published in 2018, we started in 2015 or 14 even then, right? So it takes us 2 years to build a hardware, measure it, and then top journals like JSSC takes more than a year to be published, right? But what I wanted to show is that many concepts that we did use in 112 in 7 nanometer was actually developed when we did it at 28 gigabit per second. And that kind of gave us an idea, proof of concept, and it was still valuable, that made its way to these things. And having a hardware proof gives you confidence to take it to the next level, right? Okay, so now we wanted to go beyond 200 gigabit. Obviously, just the raw data rate by increasing the clock frequency, it would not work, right? We have to go to the different modulation levels, and when we go there, what happens is that your SNR starts to drop. So the x-axis is SNR. This is the symbol error rate. And one way to read it, to get the same level of BER, 10 to the minus 6, the level of SNR that you need is much higher. And that SNR, you have to accommodate either through better equalization or through encoding or a combination of that, right? So what combination does work? That is a question. And also to understand this just reflects the reduction in the eye height. So you can think of that my signal swing from the transmitter, I can only do from 0 to VDD. If I have to encode more levels, means I'm going to chop it to smaller subsections, right? And there is a signal power penalty associated with it. But there is another source of noise, which basically means that this tiny eye is going to see the noise that comes from this large signal swing that goes from all the way from the bottom to the top, right? So the combination of these two factors will actually require an SNR compensation that is more than what is described by this theoretical plot, right? Because complete equalization or zero ISI case is not practical, right? So this is why we kind of explored different options that existed there. It will take more than a talk to go over this, so I'll just refer to this paper where we compared a pathway towards 224 gigabit per second. It's more of there is no hardware there. I just used the learning of different hardwares from our work and from other people's work to prepare a comparison table, and somehow the audience found it very useful, so they put a best paper award for this review paper. So if you're interested, you can look more into it. But for this talk, I'm going to move to a different application scenario, which is basically the chiplet or MCM. So to understand what was happening during this time in the industry, if you have a limited, like if you are limited to the periphery of the chip, then you can only have fewer number of pins and fewer number of channels. So the aggregate data rate that you can achieve is only by transmitting more through each pin. But if you open the solution space a bit such that you have an interconnect density that is 2.5D, basically from the top of the chip. So one chip is sitting here, the other chip is sitting here. They're vertically going down and then coming back to connect to the other die. Okay? In this way, you have a lot more space. You can pack more channels. You can make them even more dense, right? And that's what AMD did. That's what Intel did in their Stratix 10. So in these cases, what they're saying is that now that I have more lanes, I'm not gonna run at super high speed like 100, 200 gig. I will run at a moderate speed, 20 to 25, but I'm going to hit a very good data rate, 2 to 3 picojoule per bit. And that's what NVLink did, which is already used in their solution that shows up for Tesla, right? And this is where they said these NV links were used, not in all cases, they still had the PCI links, but the ones where they had most amount of traffic they needed, and those were highly integrated in those cases. So the link speed is around 20 gigabit per second. But the energy efficiency, everyone tries to hit 1 to 2 picojoule per bit. And so the idea is that I'm going to still hit the same aggregate data rate that you would hit with 200 gig or 112 gig, but I have more number of lanes. That's how I'm going to reach there. And because per bit energy is better here, overall I will save more. So this is more of a solution which not just relies on your SerDes technique, it relies on your interconnect advancement as well, right? And that's how this solution space occurs. Now if you look at this, it looks a bit scary how densely they could put these channels together, and these lengths are actually very small. So these four are the chips that they are cutting together. What we found is the loss is going to be much better if we are going to run only at 20 gigabit to 25 gigabit, right? So the equalization can be kept simple. So now I'm going to go back to the same plot again and see what is achievable in this case, right? And so in this case, what happens is that we revert back to the mixed signal solution, right? Because the ADC power that I pointed out, right, is gonna be huge and is gonna set the limit to how good of an energy efficiency I can achieve. And I'm gonna also do a bit of a timing recovery, and if possible, I'm gonna play tricks to freeze it somehow, right? And so if we do those, what we are saying here is the data rate is moderate. We don't need to go very high data rate because I have many interconnects to achieve the same aggregate. I want to equalization be a little simpler because it is going to be not more than 20 dB loss, just we saw in the frequency response. But I'm going to hit a very good energy efficiency because it's only energy. I don't have 4 level. SNR would be good. No additional coding latency needed, and the data rate will be flexible, like anything between 5 to 20 can be easily achievable, right? And so something that so fine-tuned or precisely designed, its portability is a bit of an issue, but that's okay. Let's say that the IPs are mature enough by the time they would be adopted, right? So what is the limit for that? And that's why it is important to put these two solutions side by side to understand a bit more on this. And so obviously the ADC and those things are gone. So that's why this part with the technologies generously improve it. And that's what the trend shows, that when you go from 14 nanometer to 16, across the data rate, you hit a much better power number. But the signaling energy is what we found is something that stands out. So why is that? To understand that, you have to see how we send the signal. Actually, what it does is that based on the logic levels, the currents are switched on one side or the other. And actually on the receiver side, the signal is sensed between two resistors. Now, if you think of it, you have two paths. So the currents is going to be always split half and half, right? So not all the current that I create here is gonna go to translate to a swing at the receiver side. But I cannot eliminate these resistors because then there will be the matching between these in the channel to the transmitter would be interrupted. So the way we do that is we kind of make the current switch on both sides. Here the current could either be pulled or no current. Now here the push-pull will make the current polarity flipped. So that achieves for the same current twice the efficiency. And we could do even further, right? And here half of the current would still be eliminated here, but this shunt termination, if it could be made a series termination, then the current that goes through this actually goes to the receiver side. So this is 4x improvement on the signaling that is still achievable. Now, if you want to push it to the farther, then we kind of introduce something where we have 3 levels of signaling, right? So X and Y are very much similar to the voltage mode signaling that we saw in the third configuration. In between, you can also turn on this switch that is gonna disconnect it from the supply, and in this mode I'm gonna consume no current. So a good example of this is shown in here. So this is where when we have the transition from 0 to 1, that's when I actually use this. 2 switches are turned on, the current is flowing this way, and then I connect it in the opposite way so that the signal reverses. And the third mode is there is no transition. Then I actually disconnect all the switches and only keep it so that things are still terminated. So if there is any reflection, it will die off, but I don't need to draw any current, and the signal is set to the mid level. So that's how we create these 3 levels. And this third mode is important because when you have a whole bunch of zeros and whole bunch of like sparse data flow, then you want to save the energy, right? And that's kind of what it shows here, that if I had a whole bunch of zeros, the signal switches back to the mid level when we don't draw any power, right? So with the transition density, a signaling power keeps on falling, drop, whereas in a traditional sense, it would stay there. It would not care where that you are sending a whole bunch of zeros that has no information in it. It would still consume power. So doing that, the equalization and other things sort of simplify. So I'm kind of running out of time, so I'll go through this a bit quicker, right? And so the long story short is that if you use that sort of property, then you can actually reduce the signaling power to a record number, right? So if you need to know some detail, then you could read this paper, which is now accepted, will probably be published in a couple of months there. And these are some link performance papers. So that brings me to the last part. So I'm gonna take 5 minutes away from the questions to go over this, but it won't take long. So the third scenario that like last 2.5 years we learned from the applications that companies like many companies, Google, Facebook, and they are making. These are like sort of smart sensors. Like if you think of the eyeglass, right? They're putting intelligence inside the eyeglass so that it can recognize people, do many things, right? And so if you tear it down, then you will see the SerDes are also going inside them, because it needs to, from the camera, it senses the data, it sends to the central processor, which kind of sits in here and do it. So what I learned from them, so by the way, I'm not putting any company's name in there because it is generic, right? So I'm not disclosing anyone's secret here, right? The data is very bursty because most of the time we are not having a conversation or we are looking in the blank, but sometimes a person shows up, then you have the activity driven, right? So long story short, it's a very bursty data pattern, right? So in that sense, we are not caring about what is the energy efficiency on bit, picojoule per bit. It's picojoule per packet. That's what they care about, right? And in that sense, we are not really, like the traditional SerDes don't do well because they're not made bursty, right? So like I have an ADC-based solution that is definitely not bursty because it takes a lot of time to run all these calibration loops and everything to converge. Even mixed signal SerDes needs a timing loop that requires to be locked. Until the clock is locked, I cannot do anything, and that already takes few microseconds, right? So basically, this is a new solution space for which you need to customize something, right? What we need here, we don't need fantastically high data rate on spectrum efficiency, but we want energy efficiency. We want bursty data. It has to be flexible, portable, and all of this, because the sensor is not necessarily, not everything goes to 7 nanometer. The sensors are actually sitting on a older technology nodes. This is sitting in 7 nanometer. The processing is obviously makes the best use of the technology advancement. And then the display is sitting on another technology node. So the portability between different technologies is important for these applications. So what we came up with is something like changing the modulation technique rather than encoding the data. For example, if I'm sending one, I'm sending VDD in one and 0 on the other. And when I send 0, I just flip them, right? I could take this into 2 edges. I could send 1 into TXP, 0 in TXN, and vice versa. So what is the benefit of doing it? The benefit of doing is a couple of things. One is the ISI, right? Because equalization gets simpler in this way. And the way we understand it, because we can send a single bit just like before, and we see these are the amount of ISI it spreads out. But in the phase domain, ISI is a lot less, right? And its polarity is also negative, which means that which has some other advantages. When we actually can, when it's always predictably negative, then I can simplify my equalization, to say the least, and keep the discussion shorter. But most important thing is that I can encode the carrier on the data bit, such that I can completely eliminate the clock recovery process. So that is where we need the locking process is gone, right? So the data comes and its carrier is encoded in it. It will retime itself. One of the simplest way to do it, if you think of it, between the rising edges, I can keep all 4 combinations, but in the falling edge, it is as such that either TXN would be ahead, TXP would be later, or vice versa. So if I take an XOR here, that will always create a pulse that can be used to retime the data. So that's how the carrier can be encoded into it, but without paying a huge overhead to that, right? And one more thing is the signaling efficiency can also be improved. And how do we do that? We do that by considering a significant difference between amplitude and phase modulation. So this blue line is amplitude modulation, and you can see that the signal goes all the way from the bottom to the top, right? So almost 1 volt peak to peak. On the same thing, because I'm sending a carrier, it's going to be attenuated, first of all. This attenuation, by the way, also impacts amplitude modulation. So the lone pulse is still as attenuated as it would be, but then the dynamic range is a lot wider. And in phase modulation, because I'm sending just always a carrier, it's just the phase relationship, the signal amplitude does not vary much. It's only going to be tiny space. And what that means is that now I can move from passive termination to active termination. Active termination means looking at the input, I'm still going to see the low impedance, but it's going to convert the signaling current to a much bigger amplitude. So that's another dimension where you improve both the signal efficiency and simplify the equalization. So the long story short, because of the time, I'm going to just skip this part of it, right? But I'll tell you that the burst mode functionality, crosstalk, in all viewpoint, it's a bit of an interesting link. And this is basically time domain signaling. If you need to see more on it, you can read this paper that explains the detail of it. And it can be extended to multi-level signaling, which also provides advantage too, right? So let me just quickly summarize what you say. So the first thing is that ML applications will not be a scenario where one size fits all. Depending on your application, you have to pick your service. If it is data center centric, obviously, you are going to be benefited from the highest speed data links, right? Be it a very short channel or a bit mid-reach or long-reach, right? And those has to be in 7 nanometer and advanced modulation. If you are somewhat on an MCM or chiplet based, then take advantage of the high integration level, put some intelligence to reduce the signaling power, and that is the way to go, and try to hit 1 picojoule per bit. Now, if you are in for smart sensors, bursty data, then I think time domain signaling is a useful concept that actually eliminates a lot of bottlenecks that is to the traditional modulation where you need to clock recovery and all of that, right? So with that, I'm gonna wrap it up now. And thanks. Now you guys can ask questions. Thank you.
All right, thank you, Professor Hossain, the great talk. Does anyone have any questions?
Okay, if nobody has any questions, you know my email address. Feel free to reach out to me if you have some questions later on. Okay.
All right, thank you again. We're gonna have a break now, and well, a couple minutes for break, and then at 2 we have our next talk by Karthik. All right, it's now 2 p.m., so let's continue on with our next speaker. Our next speaker is Karthik. Karthik, can you please share screen and take it away?
Sure. How's this for audio first? I just want to make sure audio is okay.
It is good.
Okay, perfect. Okay, and is screen sharing good now?
Yes.
Okay, perfect. So yeah, let me know when I can get started.
You can get started now.
Perfect. Okay. Cool. Hi, everyone. So my name is Karthik Ganesan. I'm a PhD student in electrical and computer engineering. This is work that was done here at UFT, advised by Professor Nadi and Rajurger. And the title of my talk is ACER, Adversarial Robustness Through Hardware-Based Stochastic Noise Injection. So at a very high level, we know that ML systems are susceptible to adversarial attacks. These are the attacks where someone can take an input that should be classified as class A, make very small changes that a human wouldn't even see as anything major, but force the network to classify them as class B. Now, prior work in the machine learning space has shown that adding noise while training and during inference helps improve the robustness against these attacks. However, current machine learning accelerators lack the ability to add such noise. So to counter this, we propose ACER, which are lightweight hardware additions to support noise injection. And ACER improves the robustness of the networks that we study by 29%, while adding less than 1% area, power, and latency overheads. So adversarial attacks, like I mentioned, are the ones that alter the inputs and cause the machine learning models to misclassify those inputs. So a classic example is this picture of a panda, and then you add some noise. And to us, the picture still looks like the same panda, but suddenly the trained network classified this as a completely different class with very high confidence. Now, you may be wondering, why does this matter? That's because machine learning is starting to get used a lot in the real world. For example, self-driving cars like Tesla, Uber, etc., use machine learning for object detection. And one example is that attacks can cause these images to be seen as a completely different sign. For example, just by adding these small patches, the stop sign is going to be interpreted as a completely different speed limit sign. Similarly, if we look at the usage of machine learning by insurance companies, increasingly, these companies are asking physicians to upload the images that they're using for the diagnosis to verify that the patients have the conditions that they're being told. And if the machine learning model used by the insurance company disagrees, they actually challenge the physician, which now creates a financial incentive for people to try to adversarially attack these images for financial gain. So here we see these sets of images which look absolutely identical to us and to a doctor as well. However, to a machine learning model, the ones on the right would be classified as a serious condition, whereas the ones on the left would be classified as benign. So like I mentioned, several prior works in the machine learning space have proposed adding noise for increasing the robustness. And techniques vary in terms of where they add this noise. For example, some techniques add this noise to the input image before it gets fed into the network. Other techniques pick a specific layer within the network and add the noise after that, while other techniques add this noise at multiple points in the network. For example, after all convolutional layers or after all convolutional and fully connected layers. So there's a breadth of techniques that have been proposed. And the other important fact is, most often the noise that these techniques add is sampled from a univariate Gaussian distribution. However, we highlight this recent work, which is called WCANet, which shows that adding multivariate noise, so noise sampled from a multivariate Gaussian distribution, can actually lead to improved robustness without sacrificing the classification accuracy, which some of these other techniques suffer from. So to motivate our hardware, we use WCANet. So what does WCANet actually do? So it adds a single noise layer before the final fully connected layer in a network. So let's take a look at a typical CNN. You have a series of convolution layers, and those are followed by pooling layers. And towards the end, you have one or more fully connected layers which produce your final output. What WCANet does is it adds this new layer in before the final fully connected layer, which adds noise. Now, the noise that is added, like I said, comes from a k-variate Gaussian distribution. And WCANet shows that k must be greater than the number of classes. So for example, if you have 10 classes, you want to use a value of k greater than this. The technical reasons are in that paper, so I won't go into the details. Shifting to hardware, if we want to implement something like this, current ML accelerators don't really support it. So what's the challenge with doing that? So if we look at producing Gaussian noise in hardware, this is quite an expensive operation. And the reason is hardware random number generators provide a uniform distribution. We can basically get a random number of bits of zeros and ones, and we put them together and we can get them to represent, signed or unsigned values within a range. But then we have to convert that into a Gaussian distribution. And the most common technique for that is this transform called the Box-Mueller transform, which we can use to convert this uniform distribution to a Gaussian one. However, as you can see, this requires a lot of very expensive operations. You need to perform a cosine, you need to perform a log, and a couple of multiplications as well. And implementing these in hardware costs a lot of gates, right? So we need about 60,000 gates to implement these, and a pretty big lookup table as well for each of these. And just as a point of comparison, the 32-bit floating point multiplier, which is what is ubiquitous in machine learning inference accelerators, only costs about 3,000 gates. So we're talking about like a pretty big difference here. And to compound the problem, WCANet, which we use because it offers the best performance, needs k units to generate noise from a k-variate distribution. So how do we solve this problem? So Acer takes a different approach to enable efficient noise injection, where instead of generating the noise, we pre-compute and store the noise points ahead of time and simply read from these stored points during inference. By doing this, we convert the problem of the expensive noise generation into a much cheaper problem of simply storing the noise. And to facilitate this storage, we add what we call a noise table in the hardware. So let's take a look at how this works. So we create this table in hardware, and because we want to access a random entry each time, because we want our noise to be random, we use the output of a random number generator, which is an RNG. And in this case, we know exactly how many entries there are in the table, and we can use the output directly from the RNG, and there's no need for us to convert anything. Now, we need to add this noise to the activations between layers. So like I showed earlier, we have the layer before the final fully connected layer, and normally that value would go through and be an input to the next layer, which would be the final layer. In this case, we add an adder here in hardware to read the value from this noise table and add it to the output before it gets sent on. Another change we make is we add a mux so that we have the flexibility to only add the noise when we want, because we don't want to go ahead and add noise to every layer, since at least for the technique we choose, we're only doing it after one layer. However, our hardware is agnostic to the noise addition technique, and if another technique needed to add noise after every layer, you would just leave this mux selected to the bottom option all the time. Now, this hardware is fine, but now the question is, how do we populate the values in this noise table? Because we can store lots and lots of points and make this noise table very large, but obviously that's going to add a lot of area overhead. But to contrast with that, if we store too few points, then it's going to reduce the security of our solution, because someone who knows these points or is able to learn these points might figure out these are the points that are being added and find a way to subvert our solution. So we need a trade-off here. So what we do is we actually choose to store lots of points in off-chip DRAM, which is much cheaper. And then each time we need noise points, we just randomly read a subset onto the chip. And to facilitate this, we modify the hardware that is used for the typical address generation in DRAM to support reading these random values. So let's take a look at how that works. So first off, DRAM addresses are typically calculated using a base address and an offset. So the base is just the start of the memory region you want to read, and the offset is just how much you increment by each time. And the value we increment the offset by, we refer to as stride. So it's very simple hardware. So we feed this stride value, we take the previous offset, and we increment this fixed value. For anybody who does CPUs, think of PC equal PC plus 4. It's really just as simple as that. Now, just like before, we also add a mux to enable this because we don't want to read random values, for example, when we're reading the weights or the inputs or anything like that. We only want to toggle this on when we're reading the noise values from DRAM to populate our noise table. So with that overview of our hardware changes, let's take a look at how this works. So we evaluate this technique using PyTorch 1.11, and we use 4 models using 2 different data sets. So that gives us 6 data points. So we pick the models and the data sets which are typically used in prior work in this space to enable a fair comparison. And we measure the robustness of our technique using the Torch attack library. And we focus on the 3 attacks, namely FGSM, PGD, and Carlini and Wagner. And we limit the noise added through each of these attacks to this value of epsilon, which is also commonly used in prior work. For a comparison, we compare against this paper, which was published in Micro 2021, which is called the 2-in-1 accelerator. And essentially what the 2-in-1 accelerator does is it trains models at several different bit widths, starting from, say, 4 bits to 16 bits. And then they pick a random model each time when they run. And they show that doing this actually increases the robustness, because for the attacker, you've made the job much harder because each time they try to adjust their attack, you're using a slightly different model. And we also retrain all of the models for each of the cases that I'm about to show you, because all these techniques require retraining the model. So first off, let's take a look at the accuracy. So on the y-axis here, I show the accuracy, and in all cases, higher is better. So we show the 6 different combinations of networks and data sets that we study. And first, we show this for classification accuracy, which is the baseline accuracy that we normally talk about when we say, the accuracy of a neural network. In addition, we also plot the robustness accuracy for the 3 different attacks that I mentioned. And robustness accuracy is what percentage of the attacked images generated by the attack does the network still classify correctly. So once again, this one also shows that higher is better. So let's start with the baseline network. This is the network that's trained as is with no defense. And we see that the networks achieve pretty good classification accuracy, at least for the C410, and reasonable accuracy for C4100. However, we see that the robustness accuracy is pretty low, and we really don't go much above 20%. And this is what we would expect because these are the baseline networks which have no defense. Now let's take a look at how this compares to 2-in-1. So we see that 2-in-1 actually improves the robustness quite a bit against all 3 attacks, but it comes at the cost of some classification accuracy. And that's just because of the mechanism that 2-in-1 uses to train. Their results just don't converge as well as the normal networks do. So finally, if we compare to our technique, we see that Acer actually is able to achieve high robustness accuracy across all 3 attacks, while still maintaining pretty much parity of classification accuracy with the baseline networks. So based on these results, we conclude that Acer is able to maintain the classification accuracy while still improving robustness accuracy over prior work. Now, one of the tunable parameters in Acer is the size of the noise table. So let's look at how we should size that noise table to reduce the area overhead while still maintaining the benefits that we see here. So similar to the previous graph, we're going to show accuracy here and all the classification accuracies. We show normalized accuracy here so that it makes it easier to do a comparison. So first off, we show the results for an unlimited table size. This is where we produce a new noise point each time and there's no storage involved. And we also show the results for a table size of 256. And from this, we see that the results are pretty much the same. And we continue sweeping it and reducing the table size in half each time. And we see that even with the table size of 128, we're okay. However, once we go to a table size of 64, we start seeing some decrease in accuracy. And then when we go to a table size of 32, we see that the accuracy diminishes even further. So based on this, we conclude that using fewer than 128 points leads to a reduction in accuracy. And so we use a table size of 128. Next, to measure the overheads of our technique, we implement our hardware on an NVDLA-based accelerator, which uses 1024 8-bit multiply accumulate units, and we run our design at a clock speed of 200 megahertz. For the RNG, we use the RNG stated in prior work, and we use their area and power numbers. And we see that when we use two RNGs, one for the latency table and one for the DRAM accesses, and those two muxes that I talked about, we add just 0.24% area and 0.58% latency overhead. Power overhead, right? And for latency, we measure this using a cycle accurate NVDLA simulator. And taking a look at the different networks, we see that across the board, we add very little latency overhead, and we add an average overhead of less than 0.001% because we're only adding noise at one point in the network. Finally, like I mentioned, we add a lot of points to the DRAM and only sample a subset. So we do a sweep to see how the parameters vary when we store more and more points. So we can go from storing 1 kilobyte in DRAM all the way up to 16. And as you can see, as we store more, we get more and more possible permutations that can be read into the noise table, which is good because that makes it harder for someone who knows these points to subvert the solution. Finally, if we look at the smallest model, which is the MobileNet V2, that takes just 2.33 megabytes. And compared to that, our storage adds only up to 0.67% area overhead, even for a 16 kilobyte list of values stored in DRAM, which increases the number of permutations to over 10 to the power 134. So to conclude, in this talk, I showed that noise injection is a promising approach to improve robustness against adversarial attacks. However, current ML inference accelerators lack a way to efficiently add such noise. We therefore propose ACER, which are a set of lightweight hardware additions to support noise injection. And for an NVDLA-based accelerator, ACER improves robustness by 29% while adding less than 1% area, power, and latency overheads. Thank you, and I'll take any questions.
All right, thank you, Karthik. Are there any questions? Okay, so let's move to our next speaker. If you have questions for Karthik, just please reach to him offline. Our next speaker is Anand. Anand, can you share your screen and take it away?
Sure. Can you see my screen?
Yeah, it's good.
Okay. Yeah, hi everyone. My name is Anand. Today I'm going to talk about our project called Arbiter, which is a numerically accurate emulator for DNN accelerators. This project is primarily driven by Chen Hao, along with me and our supervisor, Kennedy Pekimenko. So to start with, hardware accelerators for DNN training is an active area of research in computer architecture right now. So we have commonly used NVIDIA GPUs, and then later came on Google GPUs, which is specially designed for initially specially designed for DNN inference, and then later move on to DNN training. And now, if you look at the market, there are several domain-specific accelerators available for DNN training. For example, Habana, Gaudi, Cerebra's wafer scale engine, and also Huawei's DaVinci Code. And many of these hardware accelerators employ different kind of hardware level optimizations to speed up the NN training process. So one of the most common optimizations that these hardwares do is to support low precision computations. For instance, instead of using standard FP32 precision, these accelerators use half precision training or bfloat 16 or fixed point and numerous other data types. There are other optimizations like sparse computation to take advantage of sparsity in DNN training, and also approximate functional units rather than using precise functional operations, and many other optimizations. The problem with these kind of optimizations is many of these optimizations have non-trivial effect on the model convergence accuracy. So if you look at the history, let's see how low precision was supported in NVIDIA GPUs. For instance, half precision training was introduced in NVIDIA in P100 GPUs. And then people quickly realized that doing complete half precision training can significantly affect the model accuracy. And the main reason for this being, if you do, let's say, matrix multiplication on fully FP16, when you accumulate the value for the dot product, you significantly accumulate the error as well. And this keeps on growing during the training process and affects the accuracy. So in order to solve that, NVIDIA has to propose something called mixed precision training. So the idea is basically to do the multiplication and addition in FP16, but accumulation in FP32. And this seems to solve the convergence issue. But the story is not over yet. The similar issue happened again with NVIDIA's new data type called TF32, which is supported in latest Ampere architecture. The same story happened again. Like the people have found out that using TF32 can significantly affect the accuracy of certain kind of models used in HPC community. So what is the lesson from these examples? The lesson is it's really important to identify this kind of convergence issue of hardware optimizations before taping out the hardware. The earlier that you identify this issue, the better. So how do you identify these kind of issues? An obvious approach that followed in architecture community is basically to prototype these kind of hardware optimizations in cycle accurate software-based simulators. But the problem with this approach is many of the software-based simulators are extremely slow compared to real silicon. And in order to identify if there is any convergence issue with hardware level optimization, you need to train the model to its entirety. And many of the standard models take hours or even days to finish training. So running these kind of large machine learning models on software-based simulators is prohibitively slow and expensive. A second approach is basically prototyping these optimizations on FPGAs, programmable chips like FPGAs, Intel Stratix or Xilinx. But in this case, the problem is, right, in order to make a high-level machine learning model to train on these kind of FPGAs, there's enormous amount of engineering effort that you need to put into. And also often this can be extremely expensive. So in our project, what we are proposing is basically a software-based emulator. So rather than going for a cycle accurate simulator, we propose a software-based emulator for emulating these kind of hardware level optimizations. And we offer three major advantages over the existing approach. First, we emulate hardware optimization in a numerically accurate fashion. For instance, we can support emulating low precision arithmetics. We can emulate sparse computation and also approximate functional units. We also try to make it easier for users to implement these kind of hardware level optimizations. And also the emulator can be run on GPUs. So it's much faster than traditional software-based simulators, which are usually run on CPUs. So this is a work in progress. So for this talk, I'm only going to concentrate on emulating low precision training. So the key idea of Arbiter is essentially using machine learning compilers to do this kind of arithmetic emulation. Machine learning basically has raised the level of abstraction of the computation in such that like you can define the machine learning models in high-level domain-specific languages. And many of these languages are supported in machine learning compilers like TensorFlow XLA or TVM or Tensor Comprehension. They are written in hardware-independent fashion. And then the compiler progressively lowers this high-level description of the model into hardware-specific kernels. So just to take an example of how XLA compiler works. So there is a high-level DNN computation graph defined by the XLA APIs or TensorFlow APIs. And then it progressively lowered to high-level intermediate representation called XLA HLOIR, and then subsequently lowered to lower level intermediate representations like LLVMIR, and then later into CUDA kernels. Now in this compilation pipeline, the first two levels are defined as hardware in a hardware independent fashion. And the compiler progressively lowers to a hardware dependent implementation of those kernels. So what we do is essentially during the compilation process, we inject hardware specific features into the generated code, such that we can emulate these different type of arithmetic, low precision arithmetic computations in the generated kernel. So just to give an idea how you can emulate sort of a custom data type in Arbiter, the only thing that user need to provide is a sketch of the custom data type. So for instance, the sketch contains two important components. So the first one is a pair of casting function. So basically the user has to define how do you cast a floating point to the custom data type and also back. Next, the user need to provide a basic primitive mathematical operations like add, multiply, log, exponent, tanh, all those functions defined over this custom data type. So this is a pretty simple sketch that any architecture designer can provide. And once this sketch is provided, Arbiter can essentially generate code that basically uses these type of custom definition of the data type in the DNN computation. So Arbiter takes this high-level model description and also the user-defined custom data type sketch, and then it can progressively generate kernels that basically use this custom data type to basically emulate computation defined by this new data type. So as you can see in this example, we are not making any assumptions about what the data type should be. So user, depending on the user implementation, Arbiter should be able to emulate any kind of data type defined by the user. So the advantage of a system or a functional emulator like Arbiter is you can prototype different kind of precisions using Arbiter and then see how it affects the convergence of the model. So right now we are experimenting with a lot of different models and we are doing a lot of sensitivity study. So just to give an observation that we have made, we observe that if you use FP32 accumulation during custom data type during a reduced precision training, you can actually train the model using much lower precision than the standard bfloat16 or FP16 precision offered by hardware accelerators right now. So in our experiment, we found that ResNet model can tolerate up to Mantissa bits as low as 4 bits. So this is about 3 bits lower than the standard bfloat16 supported in TPUs. Second observation that we make is we conduct a sensitivity study on how different model architectures affect the convergence accuracy on low precision training. So we found that more natural language processing models like transformer can tolerate much lower data precision compared to convolution models like ResNet-50. So as you can see in this example, we basically conducted a grid search on different precision levels for floating point data type, and then found out that a transformer model can tolerate up to 5 exponent bit and 4 Mantis bit. The same precision level on ResNet-50 will not convert at all. So we are actively working on improving our emulator to support more hardware optimizations and features. For example, we are planning to support sparse computation. So this is something that NVIDIA GPUs right now support, where you have 2 to 4 structured sparsity, which can be utilized to improve the training performance. And second, many of the hardware chips use approximate functional units. For example, approximate multiply and accumulate units for approximate piecewise linear tanh functions. So we are currently working on supporting these new type of hardware optimization in the emulator. Yeah, to conclude, the main goal of this project is basically to allow fast prototyping of hardware optimizations for DNA training workload. The current approach is like using software-based simulators is prohibitively slow or require extremely high engineering effort. And in our approach, what we propose is a software-based emulator, which can emulate hardware optimizations on DNN training using machine learning compilers. And we offer numerically accurate functional emulation with minimal user effort. And also the emulation can be run on GPU. So it can be run much faster than traditional software-based simulators. Thank you for attending my talk. Happy to take any questions.
All right, thank you, Anand. Does anyone have any questions? Okay. If you think of a question later, you can reach out to Anand offline. Let's move to our next speaker. That is Alberto. Alberto, can you share your screen? And,
yeah, sure thing. Can you guys see that?
Yes, we can see your screen.
Okay. So hello, everyone. My name is Alberto Leon Ceballos. I'm from the University of Alberta, and I'm under the supervision of Dr. Hussain. Today, I will be presenting our work on the digitally assisted mixed signal multiplier accumulator unit. The main challenge for a multiplier and accumulator unit is the power consumption. As we can see in this graph here, regardless of topology, the energy consumption remains the same across for the logic units in orange, as well as the memory components seen in yellow. The main benefit of switching towards an analog computation over digital is the lower energy consumption needed in this step. So we can see the difference in the blue areas. However, this comes with its own limitations. Mainly, it would be the achievable resolution. A good indication of computational accuracy is signal to noise ratio. We can see in this graph on the left here that the digital design maintains a modest increase in energy as we increase the signal to noise ratio, whereas the analog approach for a computational unit has this exponential growth towards higher SNR. So for applications that need lower computational accuracy, that's where we find this area of opportunity, whereas the analog computation outperforms the digital in terms of energy consumption. Analog computation has been shown to be limited to about 8 to 10 bits. In our approach, we have introduced two 4x8 multipliers, and we use a shift register for the MSBs as seen here. Our approach is to use a Gilbert cell current domain multiplication, in which CapDAX set the weight and then the IDAX set the input values, respectively. The resulting values of these two are then accumulated on a voltage-controlled oscillator in the phase domain. Now, like as I mentioned in the previous slide, the weighted value scaling is set by the CapDAX, and this corresponds to the gate voltage that will be seen at the multiplier. The input value scaling is set by the different IDAX, corresponding to changing the bias currents for the multiplier, and this in turn transforms the or changes the transconductance values. The output of the current of the multiplier is then used to set the control voltage for the different oscillation frequencies. And then the accumulation we can then determine based on looking at the zero phase crossings. Now it is worthy note that the phase accumulated will have a value dependent on the nominal frequency, oscillation frequency. So if we were to take both of these oscillators differentially and we were to match these frequencies, then we could get rid of this term. When comparing our proposed design to previous works, we can see that our proposed design achieves both a good speed and resolution for the multiplier accumulation, as well as a good energy consumption as we try to reuse the current from the multiplier into the accumulation phase. Now the TDC output of the MAC unit, like I was mentioning, includes the offset factor from the nominal oscillation frequency of each of the VCOs. And when matched, this term can be removed. Now we have a calibration cycle in which the input of the multiplier is sent to common mode, and the bias current set to nominal bias. Now, depending on the error profile of the multiplier, this phase accumulation difference can then be addressed in a digital domain. We have implemented a lookup table approach for this. To address concerns such as mismatch from process corners, the VCOs are initially calibrated when powered up. Voltage variations would be addressed with voltage regulation. Now, once the system is operational, calibration can be used to account for the temperature variation that will occur during the operation. This takes place after n cycles of the multiplier unit, and then will take place for n cycles. So total cycles be the capital N cycles of the multiplier, small n representing the calibration cycles needed to bring these two phases back to matching nominal frequencies. Now this does introduce a overhead in the computation required for the matching the nominal frequencies and calibrating the units to remove this offset term. But as temperature drift is slow varying during operation, only very few calibration cycles are needed in relation to the overall cycles per computation. In this design, the main nonlinear behavior is the frequency versus current characteristic. As mentioned before, we used a shared lookup table for both VCOs containing 65 5-bit values. Now, for larger implementations, should be considered to have multiple lookup tables for co-located groups of oscillators, such that it can be matched in their nominal frequencies. Now, for machine learning applications, inference accuracy largely determines the hardware performance. We have benchmarked our design performance using convolutional neural networks, and we mainly use two data sets, the MNIST data set and the CFAR10 set. Now, for the MNIST data set, the mixed signal MAC unit achieved more than 90% accuracy with a reasonable weight value of 5 bits. When testing with the CFAR10 data set, at 5-bit weights, the digital counterpart is able to outperform the analog computation unit. However, when we increase the weight resolution and we introduce the digital correction, this vastly improves the performance of the analog computation unit, and the performance tends to reach close to the digital computation performance. And that would be the conclusion of my presentation, and I'm also open to answering any questions.
All right, thank you, Alberto. Does anyone have any questions? All right, if anyone thinks of a question, they can reach out to Alberto offline. We're gonna have a break now. It's gonna be about a 15-minute break until 3, and then we're gonna continue with our presentations. Okay, it's now 3 p.m. So let's continue with our program. Our next speaker is Anand. Can you please share your screen and take it away?
Sure. Can you see my screen?
Yes.
Okay. Hello, everyone. My name is Anand. So today I'm going to present a project called Livestream, which is a high-performance stream processing engine for periodic streams. This is a work done in collaboration with University of Toronto, Vector Institute, and Kids Hospital. So data-driven technologies are heavily used in healthcare industry right now. For instance, many data-driven models are used to do automated patient monitoring systems, also to provide personalized treatment, and also machine learning models that can do risk predictions like cardiac arrest. And many of these technologies are powered by physiological data collected from the patients. So physiological data sets contain signals like blood pressure, ECG, and EEG, and they are collected periodically in a streaming manner. For instance, blood pressure is sampled at 125 Hertz and ECG is sampled at 500 Hertz. So processing these type of high frequency data point, time series data like physiological data can often be challenging for several reasons. This first one, hospitals has to abide by a lot of data privacy protection laws. Therefore, many of these computation has to be done within the hospital facilities. And many of the hospitals only have limited access to the computing resources. Therefore, getting good performance out of limited computing resources is extremely important when you do physiological data processing. Second, many of the computation done on physiological signals require control over the time dimension of the data sets. For instance, let's take a simple example of signal normalization. And this is generally done by using a sliding window of, let's say, 10 seconds over the data stream, and then performing normalization operations within the data points that falls within the window. A more complex example would be something like a peak detection algorithm, which detects the peaks in blood pressure. So as you can see in these examples, time is an integral part of these computation, and any programming interface that you use to write these data processing pipeline need to have good support for temporal operations. So a natural question would be, what is the best framework to do physiological data processing or write the computations for the physiological data processing? The first natural choice would be to use some stream processing engine, because the data is already coming as a data stream. So in the industry, we have several popular stream processing engines like Spark Streaming, Apache, Flink, Storm, etc. And many of these languages provide a rich and powerful temporal query language. For instance, let's take the previous normalization as an example, and let's see how you write the same computation as a temporal query. So you have this input stream, and then you first define a window of, let's say, size 10 seconds. And you define two aggregate functions, mean and standard deviation. And then you join the derived mean and standard deviation back to the original stream, and then write the select operations to compute the normalized values. So in this example, you can see it's fairly simple to use this high-level query language to write these kind of computations. But the main issue with these stream processing engines is they often showcase extremely bad hardware utilization and single machine performance. So we measured 4 state-of-the-art stream processing engines and their performance on a single machine, and found that compared to hand-tuned libraries like SciPy, they often perform 1 or 2 orders of magnitude slower. Okay, the next option would be to use hand-tuned numerical libraries like Pandas, NumPy, or SciPy. So these libraries provide a large collection of hand-tuned signal processing operations. But the main issue with these libraries is they often have rigid programming interface and set of APIs that they provide, and they lack temporal language support. So it's very difficult to write physiological data processing pipelines using these kind of libraries. For instance, the developer or the machine learning engineer has to keep track of the timestamp manipulations at the application level, and this causes the user to do a lot of bookkeeping, and which basically become the data processing pipeline extremely hard to maintain and also highly error prone. So in this project, what we are trying to do is basically to bring the best of both worlds by proposing a stream processing engine called Livestream. And Livestream is specially optimized for processing periodic streams like physiological data signals. So Livestream provides rich and powerful temporal query language support similar to state-of-the-art stream processing engines. At the same time, it can achieve hardware utilization and single machine performance that is similar to hand-tuned libraries. So before getting into the weeds of Livestream, let me first explain what causes traditional stream processing engine to be so inefficient in single machine performance. So let's take one example of a stream processing pipeline. So let's say you have a 500 Hertz signal stream, and you first perform a shift operation. And then on the output, you again perform a window-based aggregation. And then finally, you join the resulting stream with another stream of 100 Hertz. Now, the first inefficiency that we observe is stream processing engines traditionally perform events in signal streams in batches of fixed size. So for instance, the shift operation takes a batch of first 8 events and then produce an output event corresponding to that batch. And then immediately issue the next operation down the pipeline to execute. So the window-based aggregation operation takes the first 10 seconds of values and then aggregate them and then produce an output and then move on to the next window. But in this case, this window cannot be executed because there are 2 events missing in that window. So the aggregation operation has to wait for the shift operation to process the next batch of events before producing the output. So this back and forth between operations significantly affect the instruction and data locality during query execution. Next issue is for the events that are already present in the window, the window-based aggregation operation has to keep them on memory before the shift operation finishes processing the next batch of events. So that means these operations need to do a lot of memory management on its own. This runtime memory allocation and deallocation significantly introduces significant runtime overhead. And finally, we observe that in the presence of discontinuous data streams, many of these stream processing engines cause a significant amount of redundant computation due to their eager execution model. For instance, if there's a gap in the 100 Hertz signal stream, the final output stream would also, there will be a corresponding gap in the final output stream as well, because the final operation is an inner join operation. So that means any computation that you've previously done on the same interval in the other side, in the other stream, are eventually going to be thrown away. So that's wasted, that computation. So this kind of redundancy causes significant overhead during runtime, and especially in case of physiological signals where the data distributions are often noisy and discontinuous. So this is a data distribution of 2 signal streams collected over a 6-month period. So in this work, we solve these problems by by taking advantage of one property called the linearity property of periodic streams. So the linearity property states that since all the data streams that we deal with in physiological data processing are of fixed frequency, every single temporal operation in the data processing pipeline follows a linear mapping between the events in the input stream and the output stream. And since all operations follow this property, you can trace this mapping throughout the entire query pipeline. And you can use this additional information to perform several optimizations that solves the inefficiencies that I described before. So for instance, the first optimization that we do is called locality tracing. So instead of performing a fixed size, instead of processing events in fixed size patches, what we do is we trace the locality of the query. For instance, let's say that the 10-second window in the final output stream has a locality trace that as shown in the illustration. You can essentially trace the linear mapping starting from the final output stream all the way to the initial input stream to figure out what is the right granularity for each operation in the query to process, such that the end-to-end locality is maximized. Second, once you have this locality or the granularity of each operation estimated, you can pre-allocate the memory required to store all those events. Because all the streams that you're dealing with has fixed frequency, and you can statically compute how many events that are going to be present in every single batch. So this eliminates runtime memory management overhead. And then finally, to solve the redundancy issue in query processing in the presence of discontinuous streams, we use this linearity property at runtime to figure out what are the regions of input streams that are guaranteed to provide results in the final output stream, and then specifically target query execution on those specific regions rather than eagerly executing on every single event in the data stream. So we implement these three optimizations in Lightstream using C# and .NET framework. And we provide several libraries and a collection of common physiological data processing operations, and also ability to integrate Lightstream with external third-party frameworks. And we primarily evaluate Lightstream against a state-of-the-art stream processing engine called Trill, and also hand-optimized libraries like SciPy and scikit-learn. And we perform the performance evaluation against real-world streaming physiological data processing applications used in Sikit's hospital. And also we use a real data collected from the patients. So in terms of single machine performance, we observe that Lightstream is able to achieve 7.5x faster performance compared to Trill, which is a state-of-the-art stream processing engine. And also for specific operations like normalization or filtering, Lightstream can actually match the performance of numerical libraries. For certain cases like normalization, it can even surpass the performance of numerical libraries. And for end-to-end performance, we observe that Lightstream can even surpass the performance of hand-optimized numerical libraries by 3.2x. We also evaluate the performance of Lightstream on two real-world streaming applications used at Sikit's hospital. So the first one is an artifact detection model called Line0, on which Lightstream is able to achieve 11 times higher performance compared to Trill. And a cardiac arrest prediction model, Lightstream is able to achieve about 5 times higher performance. So this shows that Lightstream can handle diverse data analytics requirement, at the same time provide superior single machine performance. That concludes my talk. Happy to take any questions.
All right, thank you, Anand. Does anyone have any questions? Jonas, do you have a question?
Yeah, I'm just clapping my hands.
Oh, okay. All right, if there are no questions, let's move on to the next speaker. Our next speaker is Jonas. Can you please share your screen and
Yep.
take it away?
Give me 1 second. All right. All right. Could you see my screen?
Yes.
Okay, perfect. All right, so I'm going to talk about a zest of line, which is our attempt to create an architecture-independent model distance. And this is joint work with my co-authors, Nick, Charlie, Ali, and my advisor, Nicolas Papakno. It's at the University of Toronto in collaboration with the Alan Turing Institute and the Vector Institute. So the basic motivation, the idea that we're looking for is we want to create a distance metric to compare the functional behavior, the global functional behavior of machine learning models. And why do we want to do this, right? So there are many reasons behind having a nice distance metric. It's very mathematically pleasing, but our motivations is actually quite selfish. So we do a lot of work in trustworthy machine learning. That's the direction of our lab. And the specific needs for this distance metric actually comes from our work in defending against model stealing attacks and also verifying machine and learning. So what are these things? Model stealing happens when an adversary tries to use a black box stealing attack to basically steal a victim's model. And this happens usually over publicly accessible APIs. So you have a service provider. I have some sort of, say, image segmentation model that I provide for a fee. And instead of using that service for the fee, you try to use specific queries and the outputs provided to train a local model. And then in the future, you can use that local model instead of the service. And you can also sell this local model, et cetera. So that's model steal. That's something we want to detect. And another is machine and learning, where there are regulations that now say that, for example, the GDPR requires that users have a right to be forgotten. If you provide your data to a company and they use that data to train a machine learning model, you want that data removed for your privacy reasons, then you want to provide a method for that company to unlearn your data from the machine learning model. But how can we be sure that the data point was actually unlearned and that the new model is different from the old one? Or in the case of model stealing, how can we confirm or provide some evidence for whether a model was indeed stolen from another particular victim model, as opposed to being trained independently on a similar data set? So that's why we want this distance metric. And there are some previous methods in the space that does this, but all of them were quite unsatisfactory from different angles for our use cases. The one obvious method is you compare the model's behavior on a set of inputs. So you basically compare the model's outputs on a set of inputs. And if you have a really large set of inputs that covers the entire distribution of the expected inputs, then sure, you can essentially get the global behavior. But that's quite difficult. That's quite a high bar to reach. And also, because each input point only gains you the output of the model near that point, there's a lot of variance because the behavior is very local to the output of each input point. And it's quite hard for you to pick the set of inputs that is very representative of model behavior because each part of the behavior is highly local. Another method is to say, okay, let's compare model parameters. Maybe we can say, let's just compare the L2 distance between the model weights for, say, a neural network. And this is quite attractive in the sense that, in the limit, the similarity of model weights indicates a similarity of global behavior. But this is quite limiting. This method is quite limiting for cases like model stealing because it's only applicable to models with the same architecture. You can only compare the altitude distance between two models that have the same architecture for the weights. If you distill one model into a different one after, say, you steal it, then it's very hard to run this parameter comparison. Also, you require white box access to the model if you're in suspicion of, say, a competitor, industry competitor to your service. You're in suspicion that they stole your model using a model stealing attack, and you're saying that I want to show that their model is too close in distance to ours, and you require white box access, well, it's unlikely that they're going to open up their IP, their intellectual property, for you to examine the internals of their model. So essentially what we really want here is ideally something that can compare the global behavior of ML models, yet only requires black box access and is not limited by architecture. So that's what we set forth to create. And the method that we came up with is called the zest of lime. It's a little bit play of words. We mostly apply the lime model explanation technique as a way to approximate the local behavior with linear models at different locations of the model that we're trying to compare. So the intuition is if we have a set of local behaviors that we approximate with linear models, then collectively they give us some information about the global behavior of the entire model. And the good thing of having these collections of linear models is that we can then easily compare their weights. We actually use the cosine distance to compare the weights between these collections of linear models. And using that, we create a distance. So the method overview is that we use LIME. I've cited the paper down there. It's a classic work on a way to interpret for explainability reasons a highly nonlinear model such as a neural network using local linear models. And we use that to obtain multiple linear models that capture the local behavior of the model in question around a reference set of data points. And then we compute the cosine distance between the weights of the linear models. And in practice, we show that this works quite well for our purposes. So here's the method, right? So how LIME works is essentially we learn linear models by segmenting the input space, right? Here you can see that the digits on the grape image are the segmentations that we obtain, and the specific algorithm we run is the quick shift algorithm. And we systematically ask these segments to identify which features are most influential to the classification of a data point. And in the case of image classification tasks, that means that we segment these images by masking contiguous areas of pixel. And then using the most influential features, we have LIME that learns this linear classifier, which approximates the decision boundary of the compared model near this specific data point. And then we have a reference set of data points that we use as inputs. And we take the collection of these linear models generated from this reference set of data points. We use that as an approximation of the global behavior of the compared model. So the experiments and results. So basically, given the following two classifiers, we have a reference classifier that we label CREF, and we have some sort of a reused classifier. This could be a classifier that was stolen. It could be transfer learning or knowledge distillation. It could be a model that was unlearned that was a previous model, but with a few data points unlearned from that model and retrained. And we want to compare the distance between a reference model and a reused version of that reference model versus that reference model and an unrelated model. By unrelated model, we mean a model that's trained on the same input-output distribution, however, is trained independently on a different data set. The specific domains that we run these experiments on are vision, audio, and text. For time reasons, I'm only going to show the results for the vision domain, but we have more results on audio and text in the paper itself. So it's pretty standard data sets and model architectures. The first case study that we that we run our experiments on is to detect model reuse, specifically the hard case of model extraction or model stealing. There were previous papers that looked at easier methods of model reuse in terms of detection purposes. For example, transfer learning knowledge distillation is usually a bit easier to detect. Model extraction, model stealing is a bit harder. Our method turns out to work great across all of these different settings. And these are our results. So we have here, the blue line compares a reference model and an unrelated model. And we show that the distance between these two models are significantly further than the distance between a victim model and an extracted or a stolen model that was acquired with black box model stealing or extraction attacks. And this distance is significant enough for us to detect the reuse of an ML model that was acquired by model stealing. And one question that came up quite regularly in the past was how sensitive was our method to the selection of a reference set. So in a previous slide, I talked about how we collect a reference set of data points. And using these reference set of data points, we create these linear models to approximate the local behavior linearly around these data points. And the data set, the reference set we select in these experiments is about 128 data points. And we show here that there is some deviation in terms of the model distance based on the size of the reference set that we select. But near about 128 for the Cypher 100 data set, which contains about 50,000, I believe, training points, we only need about 128 to decrease that standard deviation quite drastically to a point that we feel confident that the results are promising. And then we have a case of machine learning. And here what we have is we have this model, and we also have another model trained on the same data set, except for 128 data points that we assume has been unlearned by some unlearning requests. So say you have a model that was trained, your service provider, your users, 128 of them applied for their data points to be forgotten. You retrain your model using an approximate or train it again from scratch technique on all the other data points, except for those that have been requested to be unlearned. And we want to compare the distance between the reference data set and a model that was the reference model and a model that had been retrained from scratch, and also a model that has been retrained using an approximation technique where you try to remove the effects of those data points without actually retraining the entire model. And once again, we can show that there's quite a drastic difference between the cases of two unrelated models and models that have been directly unlearned and approximately unlearned. So when two models are approximately unlearned, we show that actually in many cases, the distance between the two models are still highly related, which shows that the effects of those unlearned data points have not been entirely removed. Whereas if you have two models that were directly unlearned in the sense that it has been retrained completely, that distance is much higher. So I'm going to conclude here. The key insights from our work are, number one, that we can learn local behaviors as comparable linear models, and then we use a collection of these linear models to approximate the global behavior of an ML model. And using that, we can create a distance metric that compares the global behavior of different machine learning models for different purposes. In the future work, we expect to find better ways to approximate local behavior more accurately with interpretable nonlinear models. And also we want to move beyond the cosine similarity, which is what we use here to compare the differences in parameters of these sets of local models. We want to see if there's any other methods that can improve their accuracy. And finally, we want to improve the selection of the reference data set for Lyme to decrease the number of reference data points that we need, or improve on finding a better set that most representatively captures the behavior of the model. And with that, I will open to questions.
All right, thank you very much. Does anyone have any questions?
How do you think this would work on transformer architectures?
That's a good question. So we have not actually run the experiments on any transformer architectures. However, we believe that the results would likely still be promising. That's actually a great direction also for future work to expand our approach to different architectures. So when we did this work, transformers weren't as prevalent in the vision domain. So that's why we picked mostly CNNs as the architecture for our vision experiments. We believe that given the I think because of the high nonlinearity of transformers and other deep learning architectures, we perhaps might need a larger reference data set if we use this current algorithm as implemented. Oh, by the way, our code is all open source in GitHub if you want to try this out for yourself and run some experiments too. But I believe the methods should still show some promise because the idea of approximating a nonlinear model using a collection of linear models would still apply to transformers.
Okay, thank you.
All right, thank you. Are there any more questions? Okay, our next speaker is Pavel. I don't see him among the attendees. So let's give him a bit ahead of schedule. So let's give him 5 minutes, see what he's gonna join.
Yes, I just want to mention that Pavel did cancel. I just checked, and sorry for not updating the schedule for that. So, Milos, is there one more person in the schedule? So maybe we can move with that talk.
No, that's it. Pavel was the last one.
Okay, perfect. So thank you all for joining today. I'm going to see you all again tomorrow at 1, which is the last day of this mini conference. As always, we're going to process the video and post it later today on the YouTube. You should have received a playlist on it. Otherwise, we'll send it again today. Thank you all for attending.
Thank you. Take care.